In this video, we're going to cover mathematical induction. How do we prove something by induction? Well, the first thing you need to understand about induction is when you're looking at examples, they all feel like one really hard math problem, maybe. But really, you follow the exact same steps for every single proof by induction. So what I'm going to do is we're going to look at examples side by side so that we can see, even though I'm trying to prove different things, I follow the same song and dance when I'm doing induction. So we're going to do side-by-side examples simultaneously to help us focus in on what the actual steps are that we're doing. Now I'm also going to use color coding to show you at each step you're interested in only pieces of the big picture. So the color coding will help us focus in on the part of the equation that we're moving around at each step. Okay, so let's get started. Here are the two equations that I'm going to try and prove. Okay, and now just to give you an example, I'll call this equation 1, I'll call this equation 2. And just so you know what's going on here, just take a step back. These are honest to goodness formulas that are telling us something. For example, now this is just an example. This formula is saying that if you add up the first 10 numbers, if n equals 10, if you add up the first 10 numbers, then that sum is going to be equal to 10 times 11 divided by 2. Okay, this is saying if you add up the first 79 numbers, that if that sum, 1 plus 2 plus 3, all the way up to plus 78 plus 79, if you add up all those numbers, that's going to be equal to 79 times 80 divided by 2. See, that's what this formula is saying. This formula is saying something a little more complicated, but it's the same deal. It is giving you a formula for something. It's saying if I add up all these things, all the way up to some point, it's actually that huge sum is actually equal to this nice, concise little fraction. Now, how do I go about proving these equations are true by induction? Well, all induction proofs start the same way. You want to show that the equation is true at some point, for some starting point. You want to show that these equations are true. I mean, if the equation isn't true at the very first number, then there's nothing to prove. So we start there. We start by proving that the formula holds for some basis step. In practice, all you're going to do is show that the equation holds for n equals 1. So how do we show that equation 1 holds when n equals 1? Well, when n equals 1, at the starting point, I'm not looking at a sum really. I'm just looking at 1 all by itself. Okay? So I'm looking at 1 all by itself on the left-hand side. What am I looking at on the right-hand side for n equals 1? Well, if n equals 1, the right-hand side becomes this. So here's the right-hand side, n times n plus 1 divided by 2. Now I plug 1 in for n. Okay, and you could just follow it along. And you end up getting that the right-hand side is equal to 1. So this equation 1 is true when n equals 1. If I plug 1 in on the left, I get 1. If I plug 1 in on the right-hand side, I get 1. So the left-hand side equals 1, the right-hand side equals 1. Therefore, this equation is true. The left-hand side equals the right-hand side. This is the step that you take when you're proving something by induction. You want to show that the equation works when n equals 1. Let's do the exact same thing over here with equation number 2. So how do I show that this equation is true when n equals 1? Well, what is the left-hand side when n equals 1? Well, the left-hand side when n equals 1 isn't a sum. It's just a single term, right? It's just going to be 1 divided by 1 times 1 plus 1. So basically 1 divided by 1 times 2. Okay, that's what my left-hand side equals when n equals 1. And this just simplifies to 1/2. What does my right-hand side equal when n equals 1? Well, my right-hand side, if I plug 1 in for n, here's my right-hand side. I'm going to plug 1 into it. I get 1 on top, and in the denominator, I get 1 plus 1. So I get 1/2. Notice what happened. I took the left-hand side, and I replaced n with 1, and I got 1/2. I took my right-hand side, and I replaced n with 1, and I got 1/2. I've just shown that this equation is true when n equals 1. Again, this is the first step you take when you're proving something by induction. You show that the equation works for some starting point. Let's go to the next step. Now I'm going to assume, now that I know that the equation actually works for at least n equals 1, what I'm going to do is I'm going to assume that the equation holds up to some step k. I know for sure it holds for n equals 1. Now I'm going to assume that it works up to some number k. And I'm going to prove that the equation will hold for the next step, k plus 1. See, if I can show that you can always go from one step to the next, then that means I can go from 2 to 3. And then once I know that 3 is true, I can go from 3 to 4. And once I know that 4 is true, I can go from 4 to 5. See, this ends up like a domino effect. It proves that these equations will hold true for any number. If I can show that if it's true up to some step k, then it always must be true for the next step, k plus 1. See, that's where the challenge is going to come in. Once I do that, it's dominoes. It takes care of itself. But I actually need to show that I can always get from one step to the next. Okay, so let's break down what this sentence is saying. So the first step, again, these are all just generic steps. The first step was to show that the formula holds for n equals 1. My next step is to assume that the equation holds up to some step k. So in practice, what that means is look at equation 1. I'm just going to take equation 1 and I'm going to replace n with k. So here's equation 1, and notice that I've just replaced n with k. So I'm assuming that the equation holds up to some fixed number k. Now my challenge is let's write our challenge equation. This is what I'm going to want to show. I want to show that I can go to the next step. So notice what I'm going to do on the left-hand side. On the left-hand side, I'm going to add another term. Okay, right now this is 1 plus 2 plus 3, blah, 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 all the way up to some fixed number k. On the left-hand side, I'm going to add the next term. So on the left-hand side, I add k plus 1, okay? So this number in blue, this expression is blue, is what I've added to the left-hand side. See, I'm trying to go to the next step. Now we need to be careful. Notice the right-hand side of my equation. This is calibrated to add up the first k numbers, okay? But now I want to be calibrated to add up to the first k plus 1 numbers. So what do? If this is the sum up to k, then how do I express the sum up to k plus 1? Easy. Notice what I'm going to do. Everywhere you see a k on the right-hand side, I'm going to replace it with k plus 1. Because I'm not adding up to k anymore. I'm adding up to k plus 1. So just take a second to convince yourself that all I've done on the right-hand side is replaced k with k plus 1. So on the left-hand side, what did I do? I added the next term, k plus 1. On the right-hand side, what did I do? Well, I replaced k with k plus 1 because I'm not adding up the first k terms anymore. I'm adding up the first k plus 1 terms. Notice this is a generic step. I'm going to do the same generic step with my equation 2 now. So let me write the assumption first. What is the assumption? Well, remember in the assumption step, I just take my equation and I replace n with k. So that's what I'm going to do. So notice, convince yourself that all I've done is I've taken my equation and replaced n with k. So I'm just saying this equation is true up to some fixed point k. Now, the challenge. Now I'm going to try and prove this domino effect. I'm going to try and prove that I can kick it up to the next step. Again, what happens on the left-hand side? Remember, on the left-hand side, I'm going to add the next term. So instead of 1 divided by k times k plus 1, I'm going to have 1 divided by k plus 1 times k plus 2. See, I added the next term. My bottom used to only go up to, my denominator only went up to k times k plus 1. So I kick it up a notch to k plus 1 times k plus 2. That's what happens on the left-hand side. You add the next step. On the right-hand side, what happens? Remember what we did? Well, on the right-hand side, you're just going to take your k. Everywhere you see a k, you're going to replace it with k plus 1. So on top, I replaced k with k plus 1, and on bottom, I replaced k with k plus 1. Okay, just take a second, make sure you You understand what we've done so far. And again, these are just generic steps. You replace n with k, and then you add